Hello. In this video we're going to be looking at solving for electromagnetic induction, which is something you're likely to encounter in your second physics course. And it can be a little tricky because it's a multi-step process and you have to be careful you're getting all the signs and directions correct. So first off, what the heck am I talking about? What is electromagnetic induction? Well, it's a very important principle in physics because it's basically how all power plants function, where you have a changing magnetic effect induces an electric effect, where a changing magnetic field can then create an electric field which will cause current to flow through, say, a wire loop. Specifically, the magnetic effect is a change in magnetic flux. Now, magnetic flux is a scalar that tells you how the magnetic field is flowing through an area. It's a dot product of the magnetic field with an area vector. The area vector has a magnitude that's just the area of whatever surface you're talking about, and the direction is perpendicular to that surface. And so a change in that magnetic flux over time induces an electric potential. You may also see this called an electromotive force, but it's not really a force, it is a potential, it has units of volts. That induced potential or voltage can then cause current to flow through, say, a wire loop, and the current that's flowing through that loop can then create a magnetic field that will oppose whatever changes were occurring in the first place. So it's a multi-step process, and what we're going to do is just break it down step by step into an algorithm. That way you can make sure you get all the signs and directions correct. So the starting point is the magnetic flux, which is a dot product of the magnetic field and the area vector. So the first thing that we need to do is define that area vector and define a direction for it. It doesn't matter if you make the direction, say, positive or negative, you just have to be consistent about it. Once you've defined that direction for the area vector, write it down somewhere because we're going to circle back to it. Once you've done that, you can solve for, say, the initial flux, the final flux, and the change in flux over time. Then your induced potential is going to be minus that change in flux over time. Now we'll look at our sign of our voltage. If the induced potential is positive, that means the induced magnetic field points in the same direction as the area vector we defined earlier. Likewise, if the induced potential is negative, then the induced magnetic field points opposite of the area vector. Once you get the direction of that induced magnetic field, point your thumb in that direction. Your hand is going to curl in the direction of the induced current that creates that field. So let's look at a couple examples where you can see this in play. So first, let's look at a case where we have a fixed area and the magnetic field is changing. So I say, okay, here's a loop of wire, it has a certain area, and the wire loop has a certain resistance. And initially, there's a magnetic field of plus 0.5 teslas in the z direction, so coming out of the screen, coming out of the board, coming out of the page. And that magnetic field decreases over 20 seconds to plus 0.1 teslas, still in the positive z direction out of the screen. So again, first thing we'll do is choose a direction for the area vector. So since our wire loop is in the xy plane, in the plane of the screen, we're going to choose an area vector that's perpendicular to the screen in the z direction. In particular, I'll say the area vector points in the plus z direction. Once I do that, I can then do the dot product where our initial magnetic field is plus 0.5 in the z direction, our area vector is the area, 0.4 meters squared, and it's in the plus z direction. So the dot product of a positive and positive z just gives you a positive scalar. Likewise, our final flux is our final magnetic field dotted into our final area, both are pointing in the plus z direction, so the dot product is positive. Then I do the change in magnetic flux over time, final flux minus the initial flux over time. I end up with minus 0.008 volts. I then say, okay, our induced potential is minus that value, so minus and negative gives us a positive voltage. And with that voltage, you can use Ohm's law, potential is current times resistance to get the current. So at least that's the number side of things. Now let's look at how we do the signs. So again, we chose our area vector to be in the positive z direction, and we found our induced potential is to be positive. Since our induced potential is positive, that means our induced magnetic field points in the same direction of the area vector, so this means our induced magnetic field points in the plus z direction out of the board, out of the screen. And since our induced magnetic field points in the plus z direction, you can point your thumb in the direction, and your hand will curl in the direction of the current flow, which in this case is counterclockwise. Without doing any math, you can also determine that this induced magnetic field has to be pointing in the plus z direction, because if our external field was pointing in the plus z and decreasing, the induced magnetic field is going to oppose that whatever change is occurring. So since our external field was, I guess, becoming less in the plus z direction, the induced magnetic field is going to make up that difference by going in the plus z as well. A really common problem you'll see in a lab physics text is where you have this U-shaped wire and a bar that's sliding across it. So let's work through how this problem works. So we have a U-shaped wire, and this red bar is sliding across it. And through this region, we have a constant magnetic field. I'll say it's minus 0.4 teslas in z. So negative z direction means it's going into the page, into the screen. And again, we'll have our wire loop in the xy plane. So let's look at how we can solve this problem. Like in the previous one, I'll say our area vector will point in the plus z direction out of the screen, out of the page. And we're essentially dealing with a rectangular loop that's just changing its width. And so we'll say, since it's a rectangle, our area is length times width. Well, we have a length of the bar that has some fixed value, and the width of the bar is changing over time. It's going to have, say, an initial width, which I'll call x0, and a final width, which we'll call xf, or a final x. And so our area is just going to be length times that width x. We can do an initial flux, which is our initial magnetic field dotted into our initial area. Our magnetic field is negative in z. Our area vector is positive in z, so that's going to give us a negative flux. And I guess I just say it's the length of the bar times the initial width x0. Likewise, our final flux is our final magnetic field, which is still in the minus z direction. Our area vector we chose to be in the plus z direction, so a negative z dotted into a positive z will give us a negative flux. And again, for the area, I say it's the length of the bar times a final x, which I'll call my width. So the change in flux over time is going to be final flux minus initial flux over time. And I've put in the values for the magnetic field and the length of the bar. And when we do that, we're left with the length of the bar, the magnetic field out front, and then on top, we have a final position minus initial position over time. Well, that's the same thing as saying our change in position over change in time. Well, a change in position over change in time is just a velocity. So it ends up being that the change in flux over time is the magnetic field times the length of the bar times the velocity. And we have all those quantities, we can get that change in flux over time. and the induced potential is the negative of that. Once you get that induced potential, you can use Ohm's law, V equals IR, to get the current going through that loop. So let's look at how we can do the signs for this. So again, I chose the area vector to point in the plus z direction out of the screen, out of the page. And we solve for the induced potential being plus 0.024 volts. So since we had a positive potential, our induced magnetic field points in the same direction as the area vector, which is the plus z direction. And we can put our thumb in the direction of that induced magnetic field. Your hand curls in the direction of the current. So since our induced magnetic field is pointing in the plus z direction, the current is going to flow counterclockwise. Again, without doing any math, you can also determine that the induced magnetic field is pointing in the plus z direction. Our external field was pointing in the minus z direction, and the area was increasing. So in a sense, more of the field was going into the screen, therefore the induced magnetic field is going to oppose it. So if we have more stuff going into the screen, the induced magnetic field is going to oppose that by going out of the screen in the plus z direction. So again, the general algorithm you'll use to solve these sort of problems is first define a direction for the area vector and keep it consistent. Then solve for your initial flux, final flux, change in flux over time. Your induced potential is going to be minus that change in flux over time. Then what you'll do is reference the sign of your induced potential back to your area vector. If your induced potential is positive, then the induced magnetic field points in the same direction as your area vector. Likewise, if the induced potential is negative, then the induced magnetic field points opposite of the area vector. Last step, when you want to get the direction of the current, point your thumb in the direction of the induced magnetic field, and your hand will curl in the direction of the induced current.